Okay, so we're ready to get started on our final module, which is going to be really an introduction to vibration. Okay, so let's take a peek at our learning plan to start. You're going to notice here that it's just one chapter. It's chapter 19. I did pull out three practice problems. One is going to be a sample problem inside of the chapter, but then I've got a couple problems for at the end of that section that we'll use to work through that'll help you then on the application problems that I have assigned. So once we have our practice problems in, you'll be ready to hand those in. And like I said, there's just three of those. Application problems, there are just three of those as well. And my hope is by going through the practice problems, that'll lead in nicely to or lead in nicely to those application problems and getting those done. I am going to go back to our learning plan and I am going to open up our PowerPoint presentation, and this will be kind of our guide through the information. During our introduction here, we're also going to be generating an equation sheet. So feel free if you want to grab out a piece of paper, we will be, creating that before we get into those practice problems. So vibrations, mechanical vibrations, they result when a system is displaced from its natural position of equilibrium. Okay, now when we were in statics, we talked a lot about static equilibrium, where some of the forces is equal to zero and we were at rest. When you were in physics, you also talked about dynamic equilibrium, and that just meant that you were at a steady state of motion, meaning you were going at a constant velocity, which means you're going in a straight line and you're not speeding up or slowing down. Okay, so you can have both dynamic equilibrium and static equilibrium. So when we're talking about a position of equilibrium, you can either be moving or you can be at rest. Okay, so either one can apply in this situation. It says here, as the forces subside from a vibration, the system tries to move back or towards that equilibrium state. So usually what has happened is something has changed. You've been knocked out of your equilibrium, whether again that is in a dynamic state or at rest, by an external force. And the system itself naturally tries to go back. And that's going to be due to what we call restorative forces. Now, those restorative forces can be the result of something natural. It's not going to be another external force. It's going to be, for instance, maybe gravity, or maybe the material itself, how stiff it is, how, not stiff it is, to try to bring it back to that original state. When we deal with vibrations, most often vibrations are not a desirable condition that we want to operate normally in. When you're driving your car, for instance, if all of a sudden something starts to vibrate, you know something is wrong. It's not operating correctly. It's not operating nice and smoothly. So most often, vibrations are going to be something we want to correct, or it corrects itself, over time. Now, that system, as it's trying to correct itself, it's developing velocities that aren't normally in the stable equilibrium state. And what ends up happening is it starts to move towards and possibly past or overshoot that equilibrium point that it's trying to re-achieve. Okay, and that's where we get what we call kind of an oscillating state back and forth until it comes back to rest at its equilibrium state. This process repeats itself, and it really tries to regain that equilibrium as it kind of moves back and forth to get there. So, and I'm kind of talking about this in the sense of I'm assuming most of you have an idea of what that means, but a very classic example of showing the behavior of vibration, and it can take a lot of different forms, but in this case, we're going to look at a spring that has a weight on it. And the way that a spring moves is very similar to any vibration. So this can be an application of a spring, but it can also be other types of applications as well. So as we look on the left-hand side here, okay, you'll notice that we have an unstretched spring, meaning we don't have any load on that spring, and this is in its kind of natural state, okay? Then what happens is we add a load to that spring. And what's going to happen is it's naturally going to deform, okay? And it's going to now be at what we call the equilibrium point. Now, in this system, it appears that the equilibrium point is at rest, okay? And so this is where it would just naturally sit based on the weight that was applied to the end of this spring, okay? Now, you'll notice that the weight is going to have, or I mean, I'm sorry, the block is going to have a weight associated with it. And then the spring is going to react to it. And the T is for tension in that spring is going to be equal to the spring rate times however far it has deformed. Now, the assumption here, and for all problems that we do for vibration, is that we are working within Hooke's law, meaning that we are in the elastic limit of our materials so that they are performing in a way that is predictable. If we ever go beyond the elastic limit of the materials or outside of the realm of Hooke's law, then all of a sudden the things that we're talking about do not apply. So that is an assumption that we are always holding throughout all of our problems. Okay. So left-hand side is a state of equilibrium. Now, on the right-hand side over here, you're going to notice that we've all of a sudden moved away from our equilibrium point. So if on the left-hand side here, this is our equilibrium point called 0, and for some reason, maybe physically pulled down, we put an external force on this and we pulled this block down a distance X. Not crazy about the variable X being used here because this is a vertical displacement. So Y would probably be better, but they're really just using it in a generic sense of distance. Okay, so don't worry too much about the direction there. So an external load has been applied and is now pulling down on that block. Now, what you'll notice is that weight didn't change, okay, but the tension in our spring has, okay? So because it's moved down further, what has happened is now we've gone past the, the natural deformation that we had at equilibrium, and we're going an additional X distance. The tension in that spring is now greater, okay? So if, for instance, imagine we're holding it down at that new position down below equilibrium, if we let go, because of the larger tension in that spring, the higher force than what the weight is, you can imagine this is going to go back up, okay? And as it goes up, because of the nature of how this is going to behave, it's going to pass our 0 point and go back up, further, okay, another distance. And then it's going to realize, oh, that's not equilibrium. I'm going to try to get back down, and it's probably going to pass it again and then continue to go up and down until it gets to its equilibrium position. So it's not going to go quite as far down. It's not going to go quite as far up for each one of the, if you would, cycles that it takes to try to find equilibrium until it does. It gets there and it gets less and less and less, and then it'll rest at equilibrium. Okay. So that is really the behavior that is going to occur as it's trying to find its natural equilibrium state again. Now, if we go to our next slide here, the motion that is taking place on the spring example that we just talked about is called simple harmonic motion. We have talked about simple harmonic motion before. Do you guys remember simple harmonic motion from any previous classes that you had with me? Anyone? It was just last term. I know there's been the Christmas break in between, but anybody remember simple harmonic motion? Kinematics. Thank you, Tyler. Yes. If you remember when we were looking at the way that we wanted a cam follower to uh, to move, that one of the options was simple harmonic motion. And what simple harmonic motion does is it takes a shape as we see here. Now, if we look at this graph, you'll notice that the x-axis, the horizontal axis right here in the middle, is our time. So as we move from left to right, this is going to be the time of our cycles of vibration. Now, as we look at this, you're going to notice a couple things. Number one, this line in the middle here, if we are not vibrating, or if we look back here, our spring is not bouncing up and down like it was on the right-hand side here. If it's sitting right at equilibrium, that is the middle line right here. Okay, so this is where we're trying to get back to all the time, or what our spring is trying to get back to. Now, you'll notice that as we start here at 0 and we go up, come back down, and go back up, that process is called a cycle, okay? And as we look at the distance between each cycle, so from one spot to the next, the same spot on the next hill and valley here, this is called a period, okay? The period is how much time does it take for me to complete one complete cycle, okay? So in order to go, if you would here, to go down, back up, and down again, that would be a period. How long does that take? Okay, and that would be in seconds, all right? The other things that we see here are going to be amplitude. Okay, amplitude is going to be how far in one direction do we move from our equilibrium position. So amplitude in one direction is going to be how far did we go? Okay, so if we go back here, that is our x distance. So from equilibrium, if I measure that x distance, that is called amplitude. Okay. And then peak to peak amplitude is just going from, one side, one distance to the other distance past equilibrium. So peak amplitude would be, for instance, from this maximum x distance all the way up to the maximum x distance up here. So as it goes past equilibrium and to its highest points in this case. Okay. There's a couple other items on here that we're going to look at. Another one is going to be frequency. Okay, frequency is going to be how many times in 1 second do we do a cycle? Okay, and I'm trying to think. There's a couple other things. So on the next pages, we are going to talk a little bit more about these relationships as well as start creating our equation sheet. And we'll go back to that harmonic motion curve and back and forth as we look at these items. So the first item that we have on our, that we're going to be putting on our equation sheet is called the period. Period is the time required for the system to complete one full cycle of motion. So again, as we go up here, it's going to be this value from one point on that curve to the very same point on the next curve. So here it's like at the top of the hill to the top of the hill. How long is that? So to get started on our equation sheet, I am going to go underneath my camera. And just as we do, for all of our other equation sheets, this is going to be our module and our chapter. So I'm going to put module 6, chapter 19, equations. Now, has anybody, besides looking at kinematics, has anybody else encountered like harmonic motion in any other courses that you've taken? Electricity classes, yes. If you've had any electricity classes, that is the foundation of AC and DC, right? Physics, did you guys come across it in physics or do a little bit of Yep, okay, very good. Yep, just physics for me. Yep, okay, perfect. So some of this period, cycle, frequency, some of these things probably sound a little familiar, but so we're gonna reapply it here in dynamics. So on that slide, that first term was period, okay? Period, again, is the time between cycles, okay? Like how long does it take for me to complete a cycle? So period is going to be the variable tau, and the equation is going to be 2 pi on top divided by what we call the natural circular frequency. And it's going to be lowercase omega and then lowercase n or sub n. okay? Now, this is just like, if you would, the same terms as angular velocity, okay? And so the units are going to be, oh, I'm sorry, they're going to be seconds, okay? Because this is radians per second down here. And then per second is going to go on the top. And because radians are unitless, they magically disappear. Our units are going to be seconds, okay? So because we have this natural circular frequency here, let's find the definition and how to calculate that, because that's going to come in handy for us. So natural circular frequency. Okay. That is going to be our omega sub n. And it is going to be equal to the square root of K over M. Okay, K over M. So over on the right-hand side here, K is familiar to us. Okay, K is spring rate. Okay. And we've talked about spring rate before, and the units for spring rate are going to be distance. I'm sorry, force divided by distance, or how much force does it take to move a unit of distance. So this is going to be in newtons per meter for metric, or pounds per foot in English units. Okay. M is going to be our traditional mass. So that's going to be kilograms, or the slug, which is a pounds times seconds squared divided by feet. Okay. And then our natural circular frequency is going to have units of radians per second. Okay, radians per second. All right. Now, spring rate, just to kind of remind us, even though we've had it before, let's we know that spring rate is going to be force divided by deformation. So P is going to be force, which we know to be newtons or pounds, pounds. And deformation is a distance, okay? So that's going to be in meters or feet, okay? So if it's given to us in millimeters or inches, we just have to be sure that we get it in the correct units to put into our equations here, okay? So let's go back. I don't know if I got ahead of myself. I did a little bit. So period, we saw the natural circular frequency. Natural circular frequency of a vibration by definition is going to be the inherent rate at which that system is going to oscillate or vibrate when it is disturbed. So this is only occurring when we're not in equilibrium, remember, okay? That's what vibrations are. And then this was kind of that section that we just looked at, okay? Natural frequency. So frequency is the number of cycles per unit of time, okay? Per unit of time. So underneath here, the next thing we're going to put is going to be frequency. So how often are these cycles happening? Okay. So frequency, that's going to be kind of this fancy F. It's going to be equal to our natural circular frequency divided by 2 pi. Now, notice it's the exact opposite of this. It's the reciprocal. So we can say that if we have our period known or figured out, we can just take 1 over the period to get the frequency as well. Okay. Now, the units for frequency are going to be the hertz. Okay. And a hertz is a cycle per second. Like how many cycles do we get per unit of time or per second? Okay. Going back, so we added this. Now we've got amplitude. Amplitude is going to be that maximum displacement. So the furthest distance that's gonna travel away from our equilibrium point. So if we go back up to our diagram here, our harmonic motion, amplitude is that distance away from, how far are we getting away from our equilibrium point? If we go back one more, it's this distance right here. So if it naturally sits at this point at zero at equilibrium and then we pull it down, this is amplitude. How far did we go? Okay. So amplitude is a distance. And it can also be equal to deformation when we don't have an external force acting. So amplitude, okay, is the distance from equilibrium. Equilibrium. It's an I in there. Okay. So XM, maximum distance, can also be equal to deformation. Okay. Where XM is equal to max amplitude. See. And those units are going to be, again, it's a distance, so it's going to be meters or feet. Now, because this is traveling back and forth, okay, we are going to be interested in how fast is that going? So what is the maximum velocity and the maximum acceleration, okay, that is going to occur? So adding those to our equation sheet. Maximum velocity is going to be V sub M is going to be equal to, we're going to take that amplitude distance because it's going to be the furthest, distance that it travels away. It's going to be where that maximum velocity occurs, times that natural circular frequency. Okay. Now we know velocity to have units of meters per second and feet per second. So those are going to be the units that we're expecting: meters per second and feet per second. Okay. And it makes sense because this is going to be in meters or feet multiplied by, as we know up here, this is radians per second. So it's going to be meters times radians is meters per second, or feet times radians, feet per second. Okay. And then acceleration. Maximum acceleration. Okay, it's going to be our A sub M is going to be our amplitude times our natural circular frequency. We're going to square that value. Okay, so this is going to be, just as we would expect, meters per second or meters per second squared and feet per second squared. Okay. All right. Back over here. So that gets us there. Now, the last part that we're going to add to our equation sheet and talk about here is going to be equivalent spring rate. So at times, we may have more than one spring working on our system, okay? And when that occurs, we can have arrangements where we have springs that are in what we call parallel. Okay, so if you've ever worked in electricity, this is a type of a circuit, a parallel circuit, and it's arranged just like this. So we can have springs in parallel where they're one next to each other, or we can have them in series, okay, or in a string, one right after another, okay? So depending on the arrangement that we have, we want to find what is the equivalent spring rate, okay, due to the arrangement that we have of two or more springs either in parallel or in series, okay? So if our springs are in parallel, that means that we're simply going to add however many springs we have in parallel on the object that we're interested in. So in this case, we've got K1 plus K2 plus K3, or however many there would be. So on the right-hand side here, we have two springs in parallel. K1 is 4 kilonewtons per meter, and K2 is 6 kilonewtons per meter. So because they're in parallel, we would simply add them together to get the equivalent spring rate. So the one spring rate that would replace those two. And in this case, it would be 4 kilonewtons plus 6 kilonewtons. So we would get 10 kilonewtons per meter. Okay, that would be the equivalent on this side. Now, over on the right-hand side, the ones that are, one like in line with one another or in series, little bit different equation. Here, we're going to take the reciprocal, K, the equivalent, and it's going to be equal to 1 over K1, 1 plus 1 over K2, and 1 over however many there would be in series, okay? So in this case, we would say, okay, 1 over K, which would be our equivalent here, is going to be equal to 1 over 4 plus 1 over 6. Okay, and doing so, when we add those together and then take the reciprocal, we're going to find that our equivalent spring rate will be 2.4 or 2,400 newtons per meter. Okay, so very different effect. So we have to be sure that we recognize the right type of arrangement that we have, parallel or series, and then apply the correct equation to find that equivalent spring rate. So let's add these two items at the bottom of our equation sheet, and then this will complete it. So I'm going to write just a little bit of a little wavy line here because this is kind of a little bit different subject than the items that are above. So I'm kind of separating it out. So I'm calling this the equivalent spring rate. Okay. And I'm going to have like two columns here, one for parallel and one for series. So parallel, okay, K, which would be our equivalent, it's going to be equal to K1 plus K2, and then I'm just going to put 3 dots. However many we would have, we would continue to add, okay? Then I'll do another little wavy line, and then this is going to be the series arrangement, and here. And this is going to be 1 over K is equal to 1 over K1 plus 1 over K2, and then dot, dot, dot to continue however many springs that we have in series. Okay. All right. So that kind of gets us to a place where we can do our first sample problem. Okay. And our first sample problem or practice problem is going to be 19.1. And it is found on page 1358 in your book. I'm going to use the illustration here, and then we will, we'll work it underneath the camera. But as you can see here, it says that we have a 50 kilogram block. It moves between the vertical guides as shown. So here's the block, and then here are the guides on either side. The block is pulled 40 millimeters down, okay, from its equilibrium position. So if we think of this as its equilibrium position, we're going to pull it down with whatever. I'm not sure if it's, with your human hands or if it's going to be with some sort of an apparatus that is going to be able to exert an external force on this to change its location to 40 millimeters below where it's at right now, which is considered its equilibrium position, okay? So what we want to do for each of the spring arrangements, so on the left-hand side, parallel, on the right-hand side, series, we want to find the period of the vibration, the maximum velocity of the block, and the maximum acceleration of the block, okay? So again, we're going to be pulling this down and then letting it go and finding the information, the 3 parts that we see here for each application, okay? So let's go underneath and get this set up, okay? So this is going to be sample problem 19.1, and this is on page 1358. 1358. All right. So information that's given to us. So from the problem, we were given the mass. The mass of this block is 50 kilograms. The spring rate of spring number one, it identified it as, and I'll kind of go back and forth here. I'll make sure. K1, which is the spring on the left-hand side, and the top spring here is 4 kilonewtons per meter. Okay, 4 kilonewtons per meter. As we know, we need everything in newtons and meters. So instead of writing 4 kilograms, I'm going to write 4,000 I'm sorry, instead of kilonewtons, 4,000 newtons per meter. Okay. And then K2 is 6 kilonewtons per meter. So I'm going to write 6,000 newtons per meter. All right. The problem also told us that we are going to move that spring 40 millimeters down, which means that would be 0.04 meters. Okay, so the distance, the amplitude is going to be 0.04 meters. Okay, we want to find, and this is going to be for each arrangement, the period, which we know to be tau. And then we want to find the maximum velocity. See, not C, part C. And the maximum acceleration. Okay. Now, what's kind of nice about these problems, like I said earlier, this is a little lighter chapter, and I think it's nice to end this way. In dynamics as our last module, it's a little bit more plug and chug. So we don't really have any sort of a diagram to create here. Okay, it's just going to be, okay, if we want to find what the period is, what's the equation for the period? And, make sure that we have either givens that we can plug in or determine what we have there. So what I'm going to do is I'm going to go back to my equation sheet and I'm going to find, all right, the equation for period is 2 pi over the natural circular frequency. So I'm just going to identify that here. Okay, so that's going to be one of the equations that I use. For maximum velocity, looking down towards the bottom, it's going to be my amplitude times my natural circular frequency. Okay, so my V max is going to be XM, or amplitude, times omega n, that circular frequency. Okay, and then my acceleration is going to be, if you remember it, it's actually easy. It's going to be that amplitude times that natural circular frequency, but we have to square it. Okay. So as we can see here, one of our common variables is this natural circular frequency. So you can imagine that's going to be the first thing that we are going to calculate, and then we'll get into finding the other items. We'll be all set. So let's do that first, and then we can use that for both parts of this problem. So our natural circular frequency is going to be equal to the square root of the spring rate divided by the mass. Okay, it's going to be equal to the square root of the spring rate divided by the mass. Okay, now spring rate. If we go back to our illustration, and I'm going to go back here because it's a little bit more clear than underneath on that paper. You're going to notice that the first one that we're going to look at here is going to be the parallel arrangement. All right, so we'll just focus over here. So we need to find the equivalent spring rate of 2 springs in parallel. Okay, so if we go underneath and we look at our equation sheet, that was this bottom part right here. We are simply going to add together the 2 spring rates that we have to get the equivalent spring rate. Okay, so for K, I'm going to say where K is equal to K1 plus K2. So that means it's going to be 4,000 plus 6,000. My K is going to be 10,000 newtons per meter. Okay, 10,000 newtons per meter. So that's going to be this value here. And then my mass is going to be kilograms underneath. Now, this is one of the few times I'm going to put the units in because and please do write this down because I do want you to go through the process here because you're going to notice we're going to have newtons per meter on top and kilograms on the bottom. And and if you recall, our units for natural circular frequency are radians per second. So I want to make sure that you see why and how we're getting that, okay? So I'm gonna put this underneath our radical, all right? And I'm gonna put 10,000 on top. Now, if you recall, a Newton expanded out is a kilogram meter per second squared. So kilogram times meter per second squared because it's mass times gravity, right? And then if that's per meter, okay, underneath, all right, that's going to be the full units there, all right? Probably going to make this a little taller. And then underneath is going to be my kilograms. So this is going to be my full radical, okay? So what I want to do is I want to make sure that underneath the radical, I get the right units. So kilograms are going to cancel out top to bottom. And because we have top to bottom here, notice that our meters cancel out as well. So we're left with nothing per second squared that we're going to take the radical. So it's going to end up with nothing per second. Or do you see how that's going to be radians per second in this case? Okay, so make sure you write this out. I want you to show that at least once so you understand that the units do come out to be radians per second in the end for our natural circular frequency here. Okay, so our number, what do you get for the number for your natural circular frequency? Oh, I should put 50 underneath here. 14.14. Yep, Tyler, I got that very same thing. So 14.14 radians per second. Okay. So this is going to be the number then that natural circular frequency that we use for all of these values. Now, this number is going to change when we do our series arrangement because our K, our equivalent K factor is going to be different than 10,000. Oopsie, I need an extra zero here. Just realized 10,000. Okay. All right, so now let's go ahead and find each one of those parts. So for this parallel springs, part A is going to be the period. So tau is equal to 2 pi over our natural circular frequency. So that's going to be 2 pi over 14.14. And this is radians per second. I'm just going to add them in there so we can kind of see how this works out. That means that our tau, the period to complete one cycle, is going to be, what do we get? You get 0.444 seconds. Yep. Thank you, Nia. Excellent. Then the next thing that we're going to find is going to be our maximum velocity. Okay. Our maximum velocity is going to be that amplitude times the natural circular frequency. So that's going to be equal to the 0.04 meters times our 14.14. Our maximum velocity, what you got? Yep, 0.565 meters per second. Maybe I should do the 0.566, huh? Down, because yours would round up. I don't have that fourth decimal in front of me. And then C is going to be our acceleration max. That's going to be our amplitude times our natural circular frequency squared. So this is going to be 0.04 again, times 14.14, and we're going to square that value. So max acceleration, what do we get? You guys get 8 meters per second squared. Just someone could please confirm.
I
That'd
did.
be great. You did too? Okay, perfect. Okay, so these are the answers for that first arrangement for the parallel springs. Any questions on those three? Okay, so continuing on, I'm gonna go to the back side here, and now we're gonna work on the series arrangement. Okay. Now, here again, we're going to use those very same equations, but as I said earlier, our natural circular frequency is going to change because our K value is going to change. Okay. So if we look back here, our second arrangement has these two springs in series or in a chain, if you would. So now we need to find the equivalent spring rate here and recalculate that natural circular frequency. So we're going to do that K first. Okay. And since it's a series, it's going to be 1 over K, which is going to be our equivalent. It's going to be equal to 1 over K1 plus 1 over K2. So that's going to equal 1 over 4,000 plus 1 over 6,000. Okay. So you're going to add those two together, then take the reciprocal, and our, I don't know if I'm going to put it here, our K is going to be equal to, let me know what number you get for your equivalent. It's 2,400. So Sarah, I'm sorry, Brooke, what you need to do is you need to take the reciprocal now of that number. You add those two together, and then because it's 1 over K, you want to solve for K, and you should get 2,400 newtons per meter. You're correct, Tyler. Verify that everybody gets that same number. Don't forget to take the reciprocal. Okay, Brooke, did you get it?
Oh yeah, I got it.
You got
Thank
it.
you.
Okay, perfect. Okay, so now that we have that number, we can recalculate now that natural circular frequency. So that's going to be the square root of our K divided by the mass. So that's going to equal the square root of, now I'm not going to redo the units for this one. So 2,400, because we already proved the units before, divided by, what's there? Oh, 50, right? Yeah, 50 kilograms. So our natural circular frequency should be 6.93 radians per second. Just want to make sure verified by someone. And once we get that verified, then we can do the period and the maximum velocity and the maximum acceleration.
I got the same thing.
You got it? Awesome. Thank you, Joshua. All right. So then our period is going to be equal to 2 pi over that natural circular frequency. how many times have I said that this class period so far? It's going to be equal to, so 2 pi on top divided by 6.93 on the bottom. Our period is going to be equal to 0.907 seconds. So this is how long it takes to do, like, if you would, one vibration up and down. Okay. Part B is going to be, what is the maximum velocity? Take that amplitude, and we're going to multiply it by our natural circular frequency for the series here. So that's going to be equal to 0.04 meters. Remember, take the meters. And we're going to multiply that by the 6.93 radians per second. Our max velocity should come out to be 2.77 meters per second. And again, just a verification to be sure my math looks good.
I got
So
it.
you got it? Okay, perfect. Thank you. Max velocity, 0.277 meters per second. So that's the velocity when we get to that 40 millimeters, or the 0.04 meters. When we pull that down and it starts going back up, that's how fast that's going to be going. Okay. All right. And then our max acceleration is going to be that same amplitude, but this time we're going to take our natural circular frequency and we're going to square it. Okay, oopsie. And make sure you use the 6.93 and square that. So max acceleration. I got 1.921 meters per second squared. Got it. Good, 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 good. Thank you, Nia. So before we leave this problem, it's nice to have the numbers, but now let's just kind of look a little bit at, how these were different. So we had the same two springs arranged two different ways, parallel and in series. So if we look at that period, okay, we look back at the first one, notice that the period on the parallel was 0.444 seconds. So if we look back at our illustration here, you're going to notice that, again, this is how much time it takes to complete one cycle or one vibration, if you would. And here it was only 0.444 seconds. And on the second one, the series, it was double that. Okay. So just by using the same springs but arranging them differently, this is a much more, if you would, spongy arrangement, where this one is going to be a more stiff. And that makes sense because our equivalent spring rate was 10,000 for our parallel arrangement, and it was 2,400 newtons per meter for our second one. So the first one is definitely going to be, if you would, more stiff. Okay. Then you'll notice that the velocity difference is here too. So max velocity, 0.566, and only half that here. And that would make sense, again, when we've got a spring rate that is so much larger, and it also is going to be a stiffer material. It's going to want to move and vibrate faster, okay? And then acceleration here, 1.92. This is the second one, series. And then 8, 4 times as much for the stiffer parallel arrangement. Okay, so interesting results, same springs, same block, same amplitude, just different arrangement of those makes a huge difference on how it behaves. Okay, any questions on this problem? All right, nice comparison there. So I am going to stop our recording.